Hey everyone, thanks for joining, thanks for being here. I'm super excited to be here. Um, Today we're going to talk about um, CI and how we solved a massive bottleneck in our CI system. This is actually a joint presentation. We have over there Etamar from DevX Infra, and he will join us in the final third of this presentation. Um, and yes, I'm Shay. Hi. Usually, those slides are like the hardest for me. What should I write about myself? And it usually boils down to I like to play video games, and that's it. This time it was a bit easier because actually, exactly 2 months ago, my wife gave birth to our first newborn. So, thank you. So, it actually means three things. That one, I'm a proud father to an adorable new baby. Two, I'm no longer a gamer. And that three, most of this presentation was built at extremely strange hours, so I hope that at least some of it makes sense. I think this is a good sentence or a good tagline to kickstart this presentation. I mean, we are going to talk about CI, and the thing is, the architecture, just like any other production microservice, it must support the current workload and future workload, right? We should be able to easily scale it out, right? And it must grow with your organization, with Wix. And like any other proper presentation, there's a problem, right? And the first part is trying to understand what the problem is and why are we even here. So I guess all of you are familiar with, with the following screenshot. It's a screenshot from GitHub status checks. The actual status names do not really matter. That's a screenshot from the Bazel CI. But you push code, right? Builds are starting to run, and you really want those checks to go green, right? As soon as possible. If they do not turn green, or even worse, they're randomly working, it hurts your flow. And we all know that as engineers, as developers, it's kind of annoying, right? It kicks you out of your rhythm. And we just want those checks to go green. It doesn't matter if you need to push an urgent fix to production, or you're just working on your day-to-day features. Things have to work, and they have to work fast. And in Wix, this is a challenge. If we're talking about the state of CI in the backend guild, in the last few years, a massive work was being put into our CI system by amazing, talented people in an effort to reduce the build time, start to finish. And just to get the basics out of the way, if you're in the backend, you probably know that Wix is working in virtual monorepo. That's VMR. That's 60 repositories of the backend guild that are being, it's basically just a vector, right, of all of Wix backend repos, and we're simulating one monorepo. Bazel is optimized to run in monorepo, and the Bazel really took our build system to a whole new level. The migration from Maven to Bazel improved the build time by 90%. That's 90, right? That's not my accent being weird. There are blogs and awesome talks at the Wix engineering website, so check them out if you're interested in hearing more. But the thing is the build time the only bottleneck? And we all know, and we saw earlier, that Wix is massively growing, right? And in the backend guild alone, we are running around 9, now maybe even 10K builds per day. The number of devs just keeps on growing, and we're bound to have more and more builds in the near future. Now, the thing is that the time that builds are spending in queue, right, before they're actually running is not great. And when I mean not great, I actually mean pretty bad. It can go up to 40 minutes, and a developer waits for his build to start, drinking 1 cup of coffee, 2 cups of coffee, 4 cups of coffee, and once the coffee runs out, eventually we get loads of sad messages in Slack. hey, what's going on? My build is not starting. What should I do? And that's not good. So this presentation is actually the tale on how, when our system's under load, how we reduced the queue time, the time that it takes builds to start, from 40, sometimes 50, sometimes even 60 minutes to just seconds. So where's the bottleneck? In Wix, we have multiple build types. If we're talking specifically about the Bazel backend flow, when a developer opens a pull request, there are several types of builds that are being fired, right? So the first one is called branch only. It's actually super simple, just running a Bazel build on your branch, right? OK. The second type is called PR merged dry run. It's a super verbose name to something that is actually very simple. It's just your pull request changes that are being rebased on top of master, right? To reflect a build that contains your changes plus latest from master. That's also very, very simple. The thing is that if you haven't rebased your branch in a while, those two checks, branch only and PR merge, might result in a different outcome because of merge conflicts and whatnot. Now the third type is the most interesting one. It's called cross-repo checks, and it allows a developer, to check breakages on the VMR before he merges his PR to master. For example, as an infrastructure developer, as a framework developer, let's say you're working on Loom Prime, on SDL, it might be a good idea to check who am I breaking if I would merge this PR to master. So a dev can choose 0 to n repos that will take part of his pull request. N, in our case, equals 60, because we have around 60 repositories in the VMR. So let's do a quick recap, right? One pull request, we have one branch only build, one PR merge build, and possibly 60 cross-repo checks. And once the PR is merged to master, we have a master build that runs Bazel on the master branch, creates an RC, and all of that jazz. So all of those builds are being routed to the same build queue. And not only pull request triggers build, right? There's also a thing called background builds. So during off-peak hours, we're checking which master branches are stale if they were not triggered using the latest VMR. And we trigger them automatically. Now, there's also a thing called trigger all master. It's out of scope. Some of you probably are aware to that. But just let's agree that we have different build types, right? Some of them are more important than others, right? Master builds are more important than background builds. You cannot argue with that. And some of them behave a bit different. They are very bursty. They're very spiky. And obviously, all of them are routed to the same queue. So let's take an example. What happens when we have two developers? They both open pull requests and runs cross-checks on all of Wix. That's around 125, 130 builds, right? And we have a developer here that wants to push a hotfix to fix a production incident. Now, in the previous state of our system, that build was most likely queued, right? Just waiting in line, and queued for a very long time. The thing is that we could not run concurrently more than 200 builds. And very simple day-to-day scenarios like the one I just described led to build storms and to the fact that everyone are just blocked. There was no way to prioritize builds. There was no way of saying, this build is more important than that build. And so we talked about Bazel earlier, right? The 90% reduction. But if the build does not start, we can't enjoy any of the Bazel goodies, right? It's like building a spaceship that does not launch off the ground. So during those incidents, everyone are blocked, everyone are sad. That's a random screenshot from of queue time of a week. We can see queue time spikes to sometimes 30 minutes, but we saw earlier that it can go up to 60 minutes. Everyone are blocked, and then we had to decide what are we going to do? We could maybe create a kill switch. When we identify those cases, let's just shut the whole thing down and say no new builds are entering the system. Or maybe just cancel builds one by one. Or even better, let's do it automatically. Create a bulk cancel API that will cancel all of the builds. Now, all of those solutions are extremely depressing solutions, and they would not solve the problem. If we want to solve the problem, we quickly understood that we need to replace our build server. Now, a quick reminder of the pieces of the puzzle that are our Bazel CI system. We have our build server, that's A, and it runs the Bazel host. Now, for increased parallelism, we have remote build executors, RBE. So builds and tests, they do not run on the Bazel host. They are being offloaded to RBE for increased parallelism. So we can have them run in a more distributed way. And we have result store that stores the output, and we can access it using UI or API. Now, this is like a game of Lego, right? We can swap one piece of the puzzle while the other remain intact. So we quickly understood that we need to replace the build server. While it is a very good solution, it was just not right for us. So we searched for a new build server, and we created a requirement document and tried to understand what does Wix need from a build server. Then we explored vendors, we conducted POCs, and eventually we chose Buildkite. Buildkite is a CI server, a build server. It met most of our requirements out of the box. It was really cool. Companies with similar scale use it as well. But the thing is, we chose a new build server. But the work only starts now, because we have two major challenges. One is building our CI system on top of Buildkite, and two is migrate everyone to the new system with no downtime. Now, you might ask yourself, why is the first challenge a real challenge? Now, let's say that you work you work on an open source project, right? Or maybe in a small company, and you integrate with a CI server. Say Buildkite, Circle CI, GitHub Actions, whatnot. You would probably use the out-of-the-box plugin that listens to GitHub commits and pull requests. You run a build, and it will automatically report back to GitHub with the results, right? Now, in Wix, that's a completely different story. We can't do that. We have plenty of different status checks, different build types. We have cross-repo checks. We're running multiple builds per commit. We have a full-blown ecosystem on top of the build server. So we need our own logic and our own services to orchestrate it. So now let's take the time to deep dive a bit on how we build our CI system on top of Buildkite. But a spoiler first. Buildkite amazingly solved the scaling problem that we introduced earlier. But moving to Buildkite, like I just said, or actually the fact that we're just moving to a new build server, it introduced a few challenges. Architecture decisions, migration dilemmas that we had to address. So let's start with those, and then get back to the scaling issues that we described. So the first thing that we want to do is to define Wix VMR, or repositories, Git repositories, in Buildkite. So that's a screenshot from GitHub, from Buildkite right there on the top. Buildkite has a building block called pipeline, right? So for every pipeline, you can define build steps that will run when that pipeline is triggered. So on the top, you can see a few repos from Wix VMR represented as Buildkite pipelines. We have editor, we have econ, we have server infra, and we have framework. There's a nice breakdown of the trend and speed and how reliable are the builds. That's just beautiful. And then we have to configure what is happening when the ecom pipeline is being triggered. So in this case, when you're running an ecom build, it will print out hello Wix engineering. And that's cool. And there's a way to actually trigger the build using an API. You post to /pipeline/ecom/builds, and then the build will start. But we don't want the ecom build to run hello Wix engineering, right? We will probably want to do some pre-build setup, download scripts, and then run Bazel, right? Bazel test // ... that runs Bazel on your working directory, and then do other magic after the Bazel run is completed. However, this is not enough. As we saw earlier, we have a lot of build types, and each one of them behaves a bit differently. So we understood that we need a way to dynamically figure out what's the build context, which build type should be triggered dynamically. So in order to solve that, we use Buildkite's dynamic pipelining. It allows us to load steps in runtime. It means that we do not hardcode Bazel test // ... We do not hardcode anything. And we can load build steps in runtime. We can start a build and then ask, well, what's the context? What should I do? And then load the steps. So using that, we can support all of the build types that we have, but it also gives us a very nice additional value. It allows us to identify certain conditions, certain feature flags, and then say, well, if we're in the ecom pipeline and the build type is pull request, I want to load those experimental steps. It's a nice way to gradually test and roll out new changes. So what I just said, it's very simple. That's the flow. There's an API call, and then there's a script that has the logic, the knowledge of which type should be triggered. And then it has, well, if I master build, please load the master.yaml for me. And it can also ask, well, if I'm in experiment mode, if a certain feature flag is open, please run experimental.yaml. So that's nice. That's a way to load all of Wix build types and test new pipelines and gradually roll out changes. But who is firing those APIs? We should also think about the migration. In Wix, we cannot allow ourselves to be down, right? And the CI system should be treated with the same care as the most critical microservice in production. So the migration should be treated with care as well. Now, in order to gradually roll out the move to Buildkite, we must have the ability to run builds in parallel, right? In the old build server and in the new build server. So we need to run all of Wix side by side and have the ability to quickly roll back. Because the last thing you want to do is to introduce a new system and go to Slack and say, hey, well, we have Buildkite, it's shiny and it's cool, and migrate specific clients, specific repos, editor, meta site, and then have them blocked because something goes wrong and you cannot roll them back easily. So this is our triggering flow. Yeah, this actually works. We're consuming webhooks from GitHub. It's push and pull request events. We are processing them and producing them to a queue. Then we have a triggering service right there at the top. Now the triggering service is responsible for the what. What are we triggering? It does not bother itself with the question, where are we triggering builds? Then it produces a message to the second Kafka topic. And then we have multiple services. We have legacy triggering service that is consuming that event and triggers builds on the old build server, on the legacy build server. And we have Buildkite triggering service that triggers builds on the new build server. Now, moving to that flow, to that architecture, proved to be absolutely crucial for the migration, because we created internally 3 different modes, right? And each repo, each repository can be in one of those modes. We have legacy mode. If a repo is defined in legacy, it means that it runs on the old build server, the legacy build server. If it runs in Buildkite mode, then builds are running on the new build server. And if a repository is defined to run as parallel run mode, it means that 2 builds are fired, right? On the old build server and on the new build server. Now the thing is that the Buildkite run would have no side effect. We are collecting metrics, obviously, and we're making sure that we have everything that we need, monitoring and BI-wise, but there's no domain event that this build happened. No RC would be created based on that build. The user won't see a link in GitHub, and overall, all of the post-build magic and downstream consumers that are usually aware that a build is finished, they won't know that anything has happened. So let's imagine how the migration can take place, and that's what actually happened. We start with dogfooding, right? We start with just moving our DevX repositories, to Buildkite mode to check for sanity, to make sure that everything is working and the rest of Wix is not changed at all. And then we take one repo. We move it to parallel run. And it means that builds are running on the legacy build server and the new build server, and again, they have no side effects. For example, if we move ecom to parallel mode, ecom won't know about it, right? They do not affect GitHub status checks, no RC would be created, they can miserably fail and burn, crash and burn, and there would be no impact whatsoever. But again, we are monitoring. DevX is monitoring what is happening. And then, once we have a bit more confidence, we can move all of Wix to parallel mode. Now, this is massive, because now we have the ability, we have the luxury of testing the load, right, and seeing how everything is working side by side without any risk, without any side effects. Now, that is real load, real traffic, where we can test the system without the users even knowing that new builds are running under the hood. And from there, everything is much simpler. We have confidence in our system. We can move, we have dogfooding of our DevX repositories, and then we can add one more repository that is not dogfooding repo and move it to Buildkite. And then gradually roll out the change to all of Wix, while still, of course, having the ability to quickly roll back when needed. So this made our life easy, migration-wise. And now let's get back to build storms, to the scaling issue. We saw that we have multiple build types, right? Each one of them behaves differently. However, all of them are sent to the same build queue, and they are frequently clogging it. What if we could assign different build types to different queues, right? What if we could have a dedicated queue for pull request builds, as they are on the critical path, and they are very, very important? What if we could have a different queue for cross-repo checks, right? It behaves weird, it's spiky. What if we could isolate it in a different queue? That's exactly what we did. We used Buildkite's queuing mechanism, and when we are firing a build, we are explicitly stating on which queue it should run. And then we did a mapping of all of our build types and a mapping of the build types to queue time, right? How fast should they start? Master builds should start as soon as possible, right? There's no argue on that. Pull request builds should start as soon as possible. Cross-repo checks, well, there's a small asterisk there. Required cross-repo checks that block the build, that block the merge if they do not pass, should start as soon as possible. But good old regular cross-repo checks should run fast, but not as important as master builds. And background builds, well, you know, since we don't have a user that is actively refreshing and waiting for his build to complete, we can tolerate a longer queue time. So we have complete isolation between all of the build types. So master builds going to the master queue, background builds going to the background queue, cross-repo checks and so on. So we have a complete isolation and now a massive invocation, for example, of cross-repo checks won't affect the critical flow, master build, pull request builds, at all. And now you probably ask yourselves, where are those builds running, right? How many pre-warmed agents do we have? How do we scale out according to the load? How do we handle spikes? So now's a good time to invite Etamar on stage, and he will join us to share some of the magic.
Thank you, Shay. Okay, so hi everyone. My name is Etamar. A little bit about myself. I love to play my guitar, currently touring the west coast of my apartment. And when I'm not on tour, I love to throw a little barbecue party from time to time. I'm on the DevX Infra team, and we are responsible for all the infrastructure underneath all CI workloads. So Fed, backends, and everything in between. So back to our agenda. What we had on the backend side of things. All builds were hosted on a SaaS solution. And at first, things were just fine. But as the organization kept growing, CI kept slowing down, and we were facing new challenges. First issue we hit was the max capacity of agents the SaaS solution was able to provide. There were just not enough agents in the pool in order to match our demand. Secondly, auto-scaling capabilities were very limited. Most of the time, we were paying for idle agents, and when we do needed to scale up, operation was just too slow, and users were frustrated. Lastly, we had one queue for all builds. As Shay explained earlier, there are multiple kinds of builds, and they were not born equally. You definitely don't want to wait for your critical hotfix build to start, just because some background jobs are spamming the queue. So, once again, went back to the lab to see how we can create a new infra that will support the load. New agent solution. We chose Kubernetes to serve as our main platform. We use it in order to schedule and manage the lifecycle of agents using jobs. Each job manages one pod that runs a CI agent. Every build starts on its own fresh pod with all the necessary dependencies on it. So when the CI job is done, the agent pod gets terminated, and the Kubernetes job is being marked as completed successfully. A basic configuration for a pod will be two containers running within the same pod. The first one will be running the agent itself, the service to connect to the Buildkite. And the second one will run a Docker in Docker container in order to enable native Docker commands from within the agents. In order to do Docker build, Docker push from within the agents, the regular CI stuff, basically. And this is the basic structure of one agent, basically. But how we can scale rapidly up and down the number of agents we are running. In other words, how we can auto-scale Kubernetes jobs. Introducing Keda, Kubernetes event-driven autoscaler. Keda is an open source, started as a collaboration between Microsoft and Red Hat, and now it's an official project incubating by the Cloud Native Computing Foundation. Keda is a single-purpose event-driven autoscaler that lets you both autoscale deployments and jobs on Kubernetes, like we do. And let's see how we can use Keda alongside Prometheus in order to create a complete autoscaling solution for CI agents. So, first step, collect data. In order to do so, we are using a service that collects the data like number of running builds, number of builds in queue from Buildkite's API, and then exposes those metrics via HTTP. Prometheus is set to scrape the HTTP metrics of that service and to store the data. Then, Keda set a query against Prometheus every few seconds, and the result of the query needs to be a number. That number will be the desired capacity of the autoscaler. After that, Keda creates the relevant amount of jobs based on the desired capacity number. So we saw the scale-up mechanism. As we just saw, it's being done exclusively by Keda. But how we can scale down? Since we cannot scale down forcefully jobs, as we might interrupt running builds and hurt users, we're doing it from the agent side. Each agent starts with a time to stop script. So if it didn't run a build for, let's say, a few minutes, let's say 10 minutes, it will automatically disconnect from the build server gracefully and will shut itself down. That way, within short amount of time, the number of running jobs on Kubernetes will match the number of desired capacity on Keda. And that's basically how we manage to scale down. And the term would be more like graceful cooldown mechanism. How can we know how many agents we need to run at each point in time in order to be also cost efficient, which is very important at our scale, and to be performant? So we have a secret formula, of course. The query we perform against Prometheus is said to be time-based. That way, we are over-provisioning the number of agents we are using based on time in day. That means there's a base amount of running agents serving as a warm-up pool. We collect the number of running builds, add them to the number of builds in queue, and then multiply it by the over-provisioning factor. So let's say we've got 10 builds running and 10 builds in queue. We'll do something like 10 plus 10, and then multiply it by 15% during peak times in order to create the over-provisioning agents to support the load. And off hours, we can use a number like 5% in order to do so. That way, we're staying both cost-efficient and performant. We're reaching the SLA that the user are expecting on peak times and off-peak times. As discussed earlier, we're using multiple queues on Buildkite. In order to support that feature from the infra side, we created separate agent pool for each queue. So basically, it lets us to set the over-provisioning factor totally different between different queues. So the issues Shay described earlier, like the PR builds and the master builds, can have totally different multi-provisioning factor. And from the infra side, we can allocate different resources for different type of jobs. So let's say I don't have to run all jobs with the same amount of CPU, memory, I/O, and stuff like that. So now we covered the full-blown autoscaler solution. I want to invite Shay back to the stage to show us the results and to wrap up this presentation.
Hey. Thanks, Etamar. It's me again. Just to get back to the question on how many agents should we actually have. Let's take a look at a real example, right? We can do a quick breakdown of the queues that we have. We discussed about them earlier, and try to figure out, well, are the builds that are running on it, are they on the critical path? If they are, maybe we should just have more pre-warmed agents, so they will start faster. If they are extremely bursty, extremely spiky, maybe we would want to have just enough pre-warmed agents to handle the first spike. And then Keda, as Etamar just described, will scale out organically. And it's like having an imaginary slider when you can choose how fast build will start running versus how much we're paying in advance. And as we have more pre-warmed agents that we pay for. So, you know, we could just throw some numbers up in the air, but how do we know that our numbers are accurate? The answer is obviously monitoring and BI. We are religiously monitoring almost every aspect in our CI system, and that is no different. Behind me, you can see graphs of monitoring the number of total agents, number of idle agents, number of busy agents per queue. We can see that during the nighttime, we have less agents for cost optimization, obviously. And we can see that per queue, we have the green line and the yellow line. The green line means number of total agents, and yellow means number of busy. And we can see the autoscaler in action because the green line is always above the yellow line. That's the autoscaler doing its magic and created new pods, new build agents. So now let's take a look at the queue time, right? The time that it takes for builds to start running. If we talk about background builds, they're less important, right? We have no pre-warmed agents for them. So build can spend in queue a few minutes. That's okay. That's completely acceptable. As we define that SLA, no user is actively waiting on the result of that build. For cross-checks, for cross-repo checks, as you know, they're not on the critical path, but sometimes they could be very spiky. Most of the time, builds are starting very, very fast. But giving a burst of builds, sometimes it takes a while for a new pod to start, for a new pod to spawn. And again, that is acceptable. However, if it is not acceptable for any reason, we can, with a single click of a button, completely eliminate that spike we're seeing here, right? We just need to add more pre-warmed agents, or maybe increase the multiplication factor that Etamar talked about earlier. And eventually, for master builds, for pull request builds, which are on the critical path, they should start as soon as possible, and we care about them the most. We can indeed see that they are starting very fast. We have a P90 of 10 seconds. So this concludes the talk of how we switched to a new build server gradually, safely, with no downtime, while solving a huge bottleneck in our system. Thank you.